Hello, and welcome to another video about linear algebra. My name is Patrick Naylor, and I'm one of the instructors for Math 235, along with Graham Turner. In this video, I'd like to discuss how to prove some of the lemmas in the additional results PDF that you can find on Learn. They have to do with identities for changing coordinates and working with the matrix of a linear transformation. If you feel like brushing up on coordinates for vector spaces, have a look at the video called Coordinates and Vector Spaces that you can find on Learn. Before we start, I want to quickly review the definition of the matrix of a linear transformation. Let V be a vector space, and suppose that we have a basis, B, consisting of elements B1, B2, all the way up to Bn for V. Further, let W be another vector space, and suppose that we have a basis C consisting of elements C1, C2, all the way up to Cm for W. Let T from V to W be any linear transformation. Then the matrix of T from B to C, or the matrix of T with respect to the bases B and C, is the matrix whose columns are the C coordinate vectors for T of B1, T of B2, all the way up to T of Bn. We write this with a T in brackets with a script B and script C on either side. This is a real M by N matrix, and it satisfies the following important identity. If X is an element of V, then the matrix of T from B to C times the B coordinate vector for X is equal to the C coordinate vector for T of X. Note that since this matrix is M by N, and the B coordinate vector for X is N by 1, this multiplication actually makes sense. Further, the C coordinate vector for T of X is actually M by 1. For the proof of this fact, or if this looks at all unfamiliar, see section 8.3 of the textbook. Something very important that I want to note here is that T is a linear transformation, but the matrix of T is actually a real matrix. T is a function from V to W, whereas the matrix of T records the action of T on coordinate vectors. They both describe the same thing, but they're different objects. This distinction is very important when you're trying to write proofs. Okay, so let's have a look at some of the lemmas in this PDF. In this video, we'll look at lemma 8.3.x, parts 1 and 4. Let V be an n-dimensional vector space, and suppose that T is a linear transformation from V to V. Let B and C be two different bases of V. Since in this case, T is a linear operator, that is, a linear transformation between V and itself, when we write the matrix of T with respect to the same bases, we'll abbreviate this by only including one side of the subscripts, and we'll just call it the matrix of T with respect to B. Okay, parts 1 and 4 say the following. Part 1, that the inverse of the change of basis matrix from B to C is the change of basis matrix from C to B. And part 4, that the matrix of T with respect to C is the change of basis matrix from B to C times the matrix of T with respect to B times the change of basis matrix from C to B. Let's warm up by proving part 1. The way we'll do this is with the following trick. To prove that two n by n matrices, A and B, are equal, it suffices to show that A times x is equal to B times x for all vectors x in Rn. This is a really useful trick, and we'll see it again in this video. Also, note that every vector in Rn is equal to the C coordinate vector of some vector x in V. I'm going to leave this to you to prove, and we'll also use this a lot. If you've been reading section 8.4, you can prove that V is isomorphic to Rn via the map, which sends a vector to its C coordinate vector. Okay, so to check that the change of basis matrix from B to C is invertible, we'll check the following. If we apply the product of these two change of basis matrices to a c-coordinate vector and use the properties of these matrices, we just get the same c-coordinate vector back. By what we've just noted, this means that the change of basis matrix from B to C times the change of basis matrix from C to B times any vector in Rn is just equal to that vector. So the product of these two matrices is the identity. In other words, we've proved that the change of basis matrix from B to C has a right inverse. Since this is a square matrix, we don't actually need to check that it's a two-sided inverse, since this is theorem 5.1.4 in the textbook. We conclude that the change of basis matrix from B to C is invertible, and its inverse is the change of basis matrix from C to B. Okay, now let's apply part 1 to give a proof of part 4. In part 4, we're asked to show that the matrix for T with respect to C is equal to the change of basis matrix from B to C times the matrix of T with respect to B times the change of basis matrix from C to B. Again, remember that when T is a linear operator, we don't write both subscripts. If you're following along, pause the video and see if you can prove this for yourself. We note that since we've just proved that a change of basis matrix is invertible, to prove this lemma, it suffices to prove the following statement, since we can multiply on the left by the change of basis matrix from C to B. If you watch the video about similar matrices, this trick might actually look familiar. Let's check what happens when we take a c-coordinate vector and multiply it on the left by each of these two products of matrices. On one hand, the change of basis matrix from C to B times the matrix of T with respect to C times a c-coordinate vector for x is just the change of basis matrix from C to B times the c-coordinate vector of T of x, which is just the b-coordinate vector for T of x. Similarly, we can check that the matrix of T with respect to B times the change of basis matrix from C to B times the c-coordinate vector for x is just the matrix of T with respect to B times the b-coordinate vector for x, which again is just the b-coordinate vector for T of x. In other words, these two products of matrices act the same on all vectors in Rn, so they must be equal. Now, since change of basis matrices are invertible, we can multiply on the left by the change of basis matrix from C to B to get the version in the lemma. This completes the proof. As I mentioned in the video about coordinates, these kinds of calculations are very important. In general, there may not be a preferred basis for an abstract vector space, so it's important to know how to do calculations in different bases. These identities will make your computations a lot easier. The rest of the lemmas in the additional results PDF have similar proofs. They rely on the properties of these matrices, which again, you should be comfortable with. As an exercise, I recommend trying to prove the rest of these results. To get a feel for how you might use these identities, I recommend looking at problem 2 in section 8.3 of the textbook. I'll also post it on Piazza and we can discuss it there. Well, that's all for now. Study hard and good luck.